Hi, good afternoon, everybody. I'm Mark Schlissel, and it's my privilege to serve as the University of Michigan's 14th president for those of you I haven't had a chance to meet as yet. But today it's my honor to be here to help celebrate faculty excellence at the University of Michigan. It's been a pleasure for me over the last 7 months to learn about the many great accomplishments of our School of Engineering. I was joking a moment ago that it seems like all of the distinguished university professors are engineers. I've met numerous faculty members, staff, students, retirees, all of whom are upholding Michigan engineering's proud tradition of excellence. I was reminded of this excellence in December commencement ceremony when NASA Administrator Charles Bolden addressed our graduates. He encouraged them to dream big dreams and reminded us all that there are many frontiers yet to be discovered. He said that members of the class of 2014 would, in their lifetimes, see a person set foot on Mars, and that the person taking the step could be sitting right there among the graduates at the Chrysler Center. That very inspiring moment is just one example of the opportunity that stems from Michigan's academic excellence and the myriad of outstanding students who study here. I know that there are countless other inspiring moments that take place in our classrooms and labs, in engineering and across the entire university. And those moments which give birth to big dreams and greater understanding of our universe are the result of faculty members who have dedicated their careers to extraordinary research and teaching at the University of Michigan. Today, we are proud to recognize one of those faculty members with a distinguished university professorship. Tamas Gombosi is a professor in the College of Engineering and the founding director of the University of Michigan's Center for Space Environment Modeling. As a space physicist, Professor Gombosi has contributed significantly to space and planetary physics, and he is revolutionizing space weather research. His accomplishments include developing the first time-dependent model of the terrestrial polar wind flowing from the ionosphere to the magnetosphere. Dr. Gombosi is also renowned for bringing scientists and science together, as he worked on a very high-profile collaboration across what was then a particularly acrimonious international border. In the 1980s, Professor Gombosi was one of the scientists working on the Soviet Union's first major international planetary mission called the Venus-Halley or Vega mission. The mission was a collaboration between the USSR, the European Space Agency, and unofficially NASA. Dr. Gombosi, who is a native of Hungary, was well known and well respected on both sides of the Iron Curtain. A news article at the time called him an international diplomat of space research. At the University of Michigan, Professor Gombosi served as chair of the Department of Atmospheric, Oceanic, and Space Sciences from 2003 to 2011 and created 2 graduate programs. He has authored or co-authored 320 articles in Science, Nature, and other leading professional journals, and served on many NASA and NSF committees. His distinguished university professorship is named in memory of Russian space pioneer Konstantin Gringauz, who worked on Sputnik 1, the world's first artificial satellite. His lecture today is entitled, My Journey in the Solar System. Friends and colleagues, please help me welcome distinguished university professor Dr. Tamas Gombosi.
Thank you, President Schlissel. Thanks everyone for coming. Today I will talk about my scientific career and some of the very interesting projects I was fortunate enough to work on. So, to start with, this is not a scientific talk. You don't have to worry about falling asleep. Actually, you do, but not because of the science I'm going to talk about. What I will talk about is how we practice science. And in practicing science, there are several very important things to remember. And this is my personal opinion, so I don't want anyone else to get in trouble for it. In my opinion, science is done the way that we reach conclusions based on incomplete evidence. And when you reach conclusions based on incomplete evidence, by definition, you cannot be right all the time. And therefore, in science, in my opinion, the batting average, just like in baseball, is the most important thing. How many times are you right and how many times were you wrong? There is no question. Every single scientist I've known always had mistakes and made incorrect conclusions. But the important thing is to recognize your own mistakes, and scientific community itself can be basically led astray by incomplete conclusions, invalid conclusions that becomes conventional wisdom. And it's very important not to fall into this category. I'd like to start by, I think I need to adjust the volume of the microphone. If I, so I am a child of the Holocaust. Both my parents survived the Holocaust. My father was very talented, but he couldn't get a university education because of anti-Jewish laws. I have a big sister. I'm very lucky that she's here today. She survived the Holocaust as a child with her maternal grandfather. And I went to school in the heart of Jewish Budapest. And our school, which is right here, was across the street from Zoltán Kodály's apartment. And he frequently visited our school. I was always sent to the back of the classroom, not to be heard. Half of my graduating high school was they were also children of the Holocaust. I call this the Phoenix generation. Most of these kids were born to parents who had their second marriage after their first families were exterminated in the Holocaust. And this really left a very strong impact on our lives. This class was pampered at home. We were spoiled, rotten, and beyond. And we were also extremely driven by our parents and our families to succeed. And we did. At least half of my high school class has at least a master's degree. And many of them are either MDs or PhDs or JDs, any combination you want. In my life, I had several mentors. And when I talk about mentors, I mean much more than just someone who introduces you to the intricacies of a scientific discipline. It's like college football. The coaches take the kids and they teach them the details of the profession, the techniques, how to do it. But the most important thing is the example they give and the doors they open. Because you can be the most talented football player if you spend your career on the bench, nobody will ever notice you. Someone has to have the trust to send you on the playing field, and then you can fight for yourself, and you better do. So my mentors were Antal Somogyi. He was in a communist Hungary, he was openly religious, which was a big negative. And he had very high moral standards, and he gave me the first opportunity in this field. The second was Pavel Eliasberg. He was a colonel in the Soviet army, in the Red Army. He was a colonel in the artillery during Second World War. And after the war, he became the leader of the Russian ballistic missile program, the targeting, the trajectory calculations. And as part of that, he was responsible for the navigation of the first Soviet spacecraft, Soviet satellites. Some of you are old enough to remember that the first Soviet moon mission, the Luna 1 or Lunik 1 as they call it, missed the moon. Not by much, but it did. Well, shortly after that, Eliasberg found himself out of the military, and he was fortunate that he was not sent to Siberia. He was sent to the civilian space program, where he became responsible for everything, data analysis, mathematics, and so on. And he discovered me in Hungary, in the backwaters of Hungary, took me under his wing, and introduced to the space scientists at the Space Research Institute in Moscow. Konstantin Gringauz is pretty much the pioneer of modern space science as we know it. He started to work on rockets in 1947. He built the radio transmitter that said beep beep for the first Sputnik. And later on he became the founder of Soviet planetary plasma physics. And Andy Nagy of Michigan, he discovered me in Hungary, and he brought me over to the US. And George Kerrigan is here, who was at that time the director of Space Physics Lab. And Andy gave me an opportunity here in this country. So a few words about Gringauz, since I selected his name as the name of my distinguished university professorship. During Second World War, he designed red tank radios, participated in the war effort, joined the rocket program in 1947, started to develop radio transmitters for the V2s. The Russians had V2s too. First rocket experiment was 1954. His group developed the radio transmitter for Sputnik 1, developed plasma instruments for Lunik 1, 2, 3, and Venera 1, and his instrument was the first to detect the solar wind. First in situ detection of the plasma sphere and plasma pulse. These are various boundaries in the magnetosphere, the terrestrial magnetosphere. The first detection of the Venus bow shock. First plasma instrument on a planetary orbiter, Venera 9 and 10. Discovery of the Martian bow shock and the magnetosphere. Plasma experiments on the Vega, the Venus Halley mission, and then Phobos mission into the planet Mars. And this shows, I intentionally selected a very informal picture of Gringauz. This is Gringauz and his wife, Irina Nikolaevna. She's still alive in Moscow. I saw her last August, and she's in her 90s. So, the first opportunity I had was before I even had my PhD. I got a master's degree in Hungary and was hired by Antal Savonyi to work on the Intercosmos 3 spacecraft, which lived, it was a radiation belt, below radiation belt investigation. And I was supposed to help to decode the data that were transmitted to Earth. Now, in these very early days, the data were transmitted in a very, very convoluted manner. Each particle counter acted like a tachometer on a car. There were various digits showing the value of the number of counts measured since the beginning of the mission. What the Russians did, they took each digit and transmitted these digits via an analog signal separately. So on Earth, you had to, first of all, you had to determine what digit it meant, and then you had to tie together the various digits to get the counts. It was a horrific, really a horrible job. I came up with an idea how to do it in an automated statistical way, and this was the work that attracted Eliasberg's attention. Eliasberg was basically the ruler of space physics data analysis in Soviet Union in those early days. Because of his military background, his reputation, his standing, he was king at IKI. IKI is the Space Research Institute. So Eliasberg discovered me in Hungary. He asked me to do a similar job with the Prognos 3 satellite. Prognos 3 was a highly elongated orbit that measured the Earth's magnetosphere. And I succeeded. And after that, Eliasberg recommended me to Konstantin Gringauz that here is a kid from Hungary. I was not even 30 at this time. A kid from Hungary who just got his PhD. Maybe he can do some useful things. So I got my second opportunity when Gringauz invited me to join his group as a postdoc at Institute Kosmiczych Исследований, Space Research Institute in Moscow. And the Space Research Institute was founded in '65, and it's a similar like the combination of JPL and Goddard. It's the lead institution of the civilian space program, even today. I arrived to IKI just a months after Venera 9, the first planetary orbiters started to orbit Venus. And this was, to me, like heaven. I mean, coming from Hungary, which had no space program, and arrived and being able to work on the most visible space program in the world at that time, that was something useful. Gringauz, when I arrived to IKI, Gringauz asked me if I wanted to work on Venera 9 and 10. I knew nothing about Venus, I knew nothing about planets, but I said absolutely yes. I always said it's fine, yes. So in addition to Gringauz, I was mentored by the best plasma physicists of the time, Roald Saggeyev, Albert Galeyev, and Vitaly Shapiro. They all came from Siberia to Moscow, and in Siberia they worked on the nuclear fusion program. Saggeyev was the director of IKI, the Space Research Institute. Galeyev was head of all space, plasma, and particle instruments, and Vitaly Shapiro was the lead theorist at that institution. And they all took me under their wing, and that's where I really learned plasma physics from them. The third opportunity came in 1977. Gringauz was not shy, to say the least, and in early 1977 he visited my institution in Hungary. And at that time I was just 30 years old, relatively new PhD. And Gringauz walked into the office of the Director General of the institution, that was the lead institute in Hungary in physics research, and made an offer. If the institute will pay my airplane ticket to the yoga meeting that was about to be held in Seattle, in the US, then Gringauz will let me give the main invited talk about the plasma environment of Venus. And this was like giving an absolute unheard of opportunity. I was a relatively new PhD, so the director agreed, and in August I really gave to a packed audience in Seattle the main results of Venera 9 and 10. And this was particularly interesting because that was the time when the US Venus probe, Pioneer Venus, was just about to be launched. So the US planetary community was extremely interested in the Russian results because that could really guide the Pioneer Venus mission. Of course, those of you who know Andy will not be surprised. After my talk, Andy came up to me and he started to talk in Hungarian. His Hungarian was a little rusty, but perfect otherwise. And he invited me to dinner. Now, coming from Hungary, where the currency was not convertible, I had $200 for 2 weeks. and I got breakfast in the dorm every morning, and that was about it. So Andy invited me to dinner to Trader Vic's, which is a chain, and that was the first meal I had in a long while. 10 years later, when I became a professor here at Michigan, I invited Andy for dinner, just to get even. In 79 and 80, there were 3 new postdocs hired in AOSS. At that time, the name was AOS. Space was not in the name yet. And just shortly before that, AOSS had a proud and impeccable history of getting rid of the most talented people in the world. The department at that time was probably the best in the world in atmospheric chemistry, including Jim Anderson, who is now professor at Harvard, Bill Chamedis, who was dean at Duke, Ralph Cicerone, who is the president of the Academy right now, John Frederick from Chicago, Sean Liu, Don Stedman, Rhys Stolarski. They all left within a short period of time. And after that came 3 new people, Tom Cravens, Tim Killeen, and I. Tom Cravens is at Kansas. Tim Killeen is the new incoming president of the UYUK system, the Illinois system. And we were basically the new group of talented young scientists. We worked very hard. Tom and I worked on Pioneer Venus with Andy Nagy. Tim worked with Paul Hayes on various terrestrial projects. On Pioneer Venus, I basically continued the work what I did in Russia. And Pioneer Venus was an orbiter that lasted 14 years. And George had an instrument on Pioneer Venus. And it was one of the most successful planetary missions ever. And we wrote a large number of papers. I'm just listing a few. We had one in Nature, several in Science, and it was really fun to work and understand how the ionosphere and magnetosphere of Venus works. 1980 came my 4th opportunity. It was right after I returned from Ann Arbor to Hungary. And at that time, there was a strong Franco-Soviet space collaboration, to some extent to rub it into the US. The French were very good at it. Still are. So they had a joint mission planned, and Jacques Blamont, Mercury, French scientist, was the driving force, and they were planning to have balloons in the Venus atmosphere. Everything was on track until in early 1980s the Russians realized that after the Venus flyby, the same spacecraft can encounter Halley's Comet. Halley's Comet is probably the most famous comet in human history, and it comes back every 76 years, and the last encounter, the last perihelion was in 1986. So Sergeyev, who was the director of IKI at that time, COSPAR was the main venue for US-Soviet space cooperation, and this was really the height of the Cold War. And during the COSPAR meeting, there was a small reception at our house. Esther and I had about 30 people over there. And Sergeyev and Blamont basically came to an agreement to modify the Venus balloon mission to Venus Halley mission to intercept Halley's Comet after the encounter with Venus. And Sergeyev invited me to participate in this mission, and this eventually became a very major Hungarian involvement. So why are comets so important, or why are we so interested in comets? The early solar system, the formation of the solar system, in some respect is like building a house. As the pre-solar nebula slowly rotates, the small velocity differences between particles result that these particles can come together and stick together. And they build up so-called planetesimals. And eventually these planetesimals become bigger and bigger, and they form the planets. We know from our own experience that no construction ever finishes with using up all the available materials. There is always leftovers. Now, this leftover junk in the solar system is what we call comets. They were gravitationally ejected out to beyond Pluto's orbit, and these are the so-called trans-Plutonian objects. And that's the source of most comets. So in some respect, comets carry the most pristine materials and information about the formation and about the early solar system. That's why we care so much about comets. So the Vega mission was a very sophisticated spacecraft by those standards. And that was the first international mission organized by the Russians. Roald Sergeyev, the director of IKI, was a personal college friend of Mikhail Gorbachev. And later, Sergeyev became the science advisor to Gorbachev. So, Sergeyev started to experiment with glasnost before Gorbachev started glasnost. So, in some respects, some experimental political overtures were done in the early 1980s with the Vega mission. And because I was relatively known both in the US and Europe and here in Russia, Sergeyev used me as one of his ambassadors in this endeavor. So I became one of Sergeyev's ambassadors, and the highlight of my political activities was that in November 1982, on Sergeyev's behalf, I gave the first public talk about the Vega mission. And it was in the US, and it was in Washington, organized by the Planetary Society. And there were 3 speakers, Isaac Asimov, Carl Sagan, and I. Now, I was young enough, cocky enough, and unfamiliar enough with US science that I didn't really realize what kind of an environment I was thrown into. Later on, in September '83, the International Astronautical Federation held its annual conference in Budapest. And many of you were not even born then and don't remember, but September 1, the Soviet Union shut down a Korean airline. And this conference was about a few weeks afterwards. And 1983 was the time, the year when both Salyrai and the second Soviet female astronaut, Svetlana Savitskaya, were flown in space. And they were both in Budapest at this meeting. But NASA, because of the politics, basically canceled all joint appearances. Now, astronauts, and we know a few astronauts here in Michigan, astronauts are not selected for not being inventive. So Sally Ride decided that the heck with NASA, she wanted to meet with Svetlana. So she asked me to organize a quote-unquote secret meeting between the two of them. Now, of course, nothing was secret in Hungary. The Russians were more than happy to oblige. The Hungarians were more than happy to help. So I managed to organize this meeting in the apartment of Bertalan Farkas. And here are my celebrity pictures. It just shows how young we were. So this is after the presentation in Washington with Asimov and Carl Sagan and Frank Press. Many of you remember Frank. And this was the quote-unquote secret meeting with Sally and Svetlana. And Sally was very grateful for this for the rest of her life. We stayed in touch. And I became friends with Carl Sagan until his untimely death. So, in 1986, we encountered Comet Halley, and basically this was the first time that we learned something about the comet. There were several flybys. There was a Halley Armada. The Europeans had their first deep space mission called Giotto, after Giotto di Bondone, who painted Halley's comet. The Soviets had 2 Vega spacecraft, and the Japanese had 2 spacecraft too. So there were 5 spacecraft encountering Halley, and this is pretty much the best quality picture we had about Comet Halley, because it was very active. There was a lot of dust cloud, gas and dust around it, and Harry Hoopis and I published a paper in Nature about our idea of how comets work. This was a lot of fun. By the way, try to remember this picture when I will show the images we recently got from comet Churyumov-Gerasimenko. So after Vega, I came back to the US, again, on this invitation. Dynamics Explorer, again, George was part of it, Paul Hayes was part of it, Andy Nagy was part of it. And I started to work on Pioneer Venus, Dynamics Explorer data, did some theoretical work, and this is when I did the first time-dependent polar wind model, which describes the transonic outflow of ionospheric charged particles into the magnetosphere. And this was, again, a lot of fun. At this time, I remember in 1979 when I arrived to the US the first time. A few weeks later, the FBI visited me in the office and asked, "Are you a spy?" That was their first question. I didn't know what to say. I mean, if I say yes or no, whatever. So this went on. The guy visited me a few times. But in 1985, we applied for permanent residency. And a few weeks later, the FBI guy called me to an off-campus meeting. And at this off-campus meeting, he introduced me another guy who just showed a badge. I was too scared to remember. And he basically wanted to recruit me to go back to Moscow and spy for the US. I was scared less. I basically had no clue what to do. Fortunately, I turned to the university, and Bill Kuhn was the department chair at that time, and Jim Dudestadt was the dean. And Jim basically called FBI and said to back off. So, but whoever the agent was kept his promise, and I was put on the excludable alien list, which is basically people who can be excluded from the US for no reason. And I had secondary inspection until we became US citizens in 1992. So this was not a pleasant experience. But then came the 5th opportunity in my life. The largest NASA instrument contract at Michigan ever was the UR's spacecraft, the Upper Atmosphere Research Satellite, and there was a high-resolution Doppler imager, which was, the PI was Paul Hayes. At that time, over the years, the total development cost, I think, was about $25 million. George can correct me if I am wrong. It would be over $50 million today. In the middle of the development phase, Paul Hayes was recruited by NCAR, that's the National Center for Atmospheric Research in Boulder. And the university decided, Jim Dudestadt decided to make a counteroffer and a retention package. And part of the retention package was a tenure-track hunting license for space physics. Now, Hayes wanted to hire Tim Killeen because Tim was working in his. Tom Donahue, Andy, and George can tell the details of the story if he decides, convinced the dean, at that time he was Chuck West, to hire both Killeen and myself. So from that point on, until Tim left the university, Killeen and I were treated as twins. Our salary was always within $1,000 of each other. The college made sure that when one got a promotion, the other got it too, and so on. After I became faculty, teaching faculty, I had 31 postdocs and PhD students. One unfortunately deceased, Dick Kanata. Out of the 30 who are alive, there are 8, 25% approximately, who are tenure-track faculty, 24 are in space science, and 7 are in AOSS, and only 4 are in non-research, and one of them, according to his own admission, is fiercely rich. He is writing trading softwares for Wall Street. Presently, I have 7 postdocs and students. I wrote 2 graduate-level textbooks, and I wrote a book about our family history and my career. And I decided to do it because most immigrants pretty much immigration loses the heritage of the family. So in '91 came my 6th opportunity. Since 1982, the European Science Foundation, the European Space Agency, and NASA worked together on a very ambitious flagship mission to the planet Saturn and its moon Titan. In 1990, the announcement of opportunity was released, and 91 the science teams were selected, and I was selected as interdisciplinary scientist for magnetosphere and planetary and plasma science. And basically, I am working on Cassini since 1991, and end of mission will be in 2017, September 15th. The spacecraft will plunge into the deep atmosphere of Saturn, and end of mission is 6 months later. So this is almost like a scientific lifetime. Some Cassini highlights, and I really don't want to make this into a science talk. I'm worried that you guys will fall asleep. It's time. There are several really important discoveries. Cassini discovered that Saturn has no fixed rotation rate. There are several rotation rates that vary with time and different for the northern and southern hemispheres. And this contradicts to everything we ever know about dynamo theory. So this is really a puzzle that we are still working on. Cassini also discovered that Enceladus is the engine of the Saturnian system because Enceladus ejects as much water per second as a very active comet. And this is pretty much that drives the whole Saturnian magnetosphere. And interestingly enough, this was discovered by the magnetometer. The fact that Enceladus is emitting that much water. starting in 2017, Cassini will enter its final set of orbits, and it will go very, very close, a few thousand kilometers above the 1 millibar level. And we are expecting a lot of new discoveries, and Cassini is just sheer fun. Later on, I started to work on space weather. Space weather is basically the conditions in space that affect technological systems or human life or human health. And space weather, of course, originates from the sun, because solar activity drives the plasma environment, and therefore the electrodynamic environment near the Earth. This schematic shows some of the impacts from astronaut safety to GPS accuracy to radiation dose obtained by airline crew and passengers, communications, but the most important or most expensive danger of space weather is the power. In the power grid, each transformer station that costs tens of millions of dollars, they are individually designed. If by space weather one station is burned down, and it happened before, then it takes 6 to 12 months to restore it, rebuild it again. So the biggest impact of space weather is not the actual damage, it's the time delay between the damage and the time when full power is restored. And this can be in the trillions of dollars, according to the National Academy of Sciences study. So space weather is becoming a very important component of the national critical infrastructure. And it's dealt with at the presidential level. Here in Michigan, over the last 15 years, we developed probably the most sophisticated numerical simulation methods for space weather. And I would like to show this movie. It's a two-dimensional cut through a three-dimensional simulation, which shows the white lines are interplanetary magnetic field lines. This black circle is the sun. And you can see the scales. They are in solar radii. So at t equals 0, we launch a so-called coronal mass ejection. That is the main source of space weather. And watch the simulation. So the CME, the coronal mass ejections, propagate out at 60 RS. The 60 solar radii is Mercury. And it keeps moving and highly distorts the interplanetary structure until we arrive to 215, which is Earth's orbit. And there, the grid, this is adaptive mesh refinement. So we just start to zoom in our simulation. We have 16 levels of refinement in this simulation. And it takes 16 levels to go from the solar scales to a terrestrial scale. It really makes you humble to see how tiny we are in this solar system. And of course, the solar system is even tinier. Now, in early 2000s, the American Museum of Natural History, together with the Hayden Planetarium, created a planetarium show called Journey to the Stars. And they have very high standards. And this show, by the way, was seen by over 1 million people. To do this planetarium show, which is 20 minutes, they used the most realistic real measurements and most realistic simulations to create. 3.5 minutes of this video is based on our simulations. So they took our simulations and combined it with Hollywood-type visualization magic. This planetarium show was narrated by Whoopi Goldberg. According to the license agreement, we can use in presentations the video, but not the song. So I replace the sound with music, and I give extra credit to whoever recognizes the music. Bram. Mission I'd like to talk about is Rosetta. Rosetta is an ESA mission which was launched in 2004. It took 10 years for Rosetta to reach Comet-Shorium of Gerasimenko, and Rosetta got its name from the Rosetta Stone, because this mission is supposed to take a chemistry laboratory to the comet and solve the mysteries of the origin of the solar system. It is supposed to be the bilingual text, as the Rosetta Stone was. This is where the name comes from. So it just landed the lander in November. It was a partial success, but we got some very interesting data. In August this year, we will have perihelion, and December 2015, we will have the official end of mission, and Rosetta will, in August next year, Rosetta will reach 3.5 astronomical units, 3.5 times further than the Earth, and at that point we will lose communication. So, this is the Rosetta spacecraft, and it has some very detailed, fantastic images of the nucleus. But space scientists are somewhat irreverent and have great imagination. So some people started to draw additions to the comet nucleus, and we decided that in effect this comet nucleus is a rubber duck, and we call it the rubber duck. And that's the official name, by the way, at least within the project. Here in Michigan, we do a lot of modeling for the Rosetta mission. Again, I don't want to go into details, but the illumination, which is shown with the color code on the nucleus shape, pretty much determines the variation of the gas production rate. And these curves show the black is the observation, the red, green, and blue are model results. We can really reproduce very well the observations. I just want to talk about one thing with respect of Rosetta, and this is our paper which was published in Science not long ago, which determined the deuterium to hydrogen ratio in the outgassing of in the coma of the comet. This line here is the deuterium to hydrogen ratio at Earth. This is in the protostellar nebula, and the giant planets, Jupiter, Saturn, and so on, are pretty much this ratio. These are the so-called Oort cloud. This is the comet cloud, which is very, very far away from the sun, about 1 light year away. And this is the Jupiter family comets. This is where Churyumov-Gerasimenko belongs to. Previous remote sensing instruments pretty much said that these Jupiter family comets have very similar D/H ratio as Earth does. And that's when the conventional wisdom that the oceans on Earth come from these kind of comets. Now, add Churyumov-Gerasimenko, and this ratio in Churyumov-Gerasimenko is about 3 times higher. So we managed to basically change the conventional wisdom. Now we are back to the point where we don't know, which is in science called advanced. So, in summary, I'd like to go through some lessons I learned. My number one lesson was always grab any opportunity, even if it's outside your comfort zone and your expertise. You will swim or sink. My second is mentoring is critical for the health of any scientific field. Appreciate your mentors and repay them by mentoring the next generation. And mentoring, as I said at the very beginning, is more than just teaching the details and the techniques of the field. Mentoring is opening doors for the young people. You are not entitled to anything. The world doesn't owe you anything. I heard people in my profession saying, I have a PhD, if the world wants me to do space science, the world has to fund me. Well, I have news for you. Nobody cares. If you want to do what you like to do, you have to fight for it. And last point is we are in this business not for the money. So if you don't enjoy it, don't do it. Getting a PhD is hard work, and I've seen many, many disappointed PhDs in my life. It's not worse if you don't feel complete dedication. So finally, I'd like to thank my family, of course. This is when our children were little. This is my daughter and her 3 sons, my son and his 2 daughters, and of course the 5 little gangsters who give us so much pleasure. So this is my final slide, and I'm still having a lot of fun, and I'm planning to keep doing it. Thank you very much.
There's 8 satellites, and they're all deployed in a single plane, equally spread all the way around the Earth. And the reason they're so small compared to typical weather satellites is because of